I'm putting down the augmented matrix for this linear system. So we have the first two equations, and then the third one is negative 3a plus b and 1. Is that what everybody's getting? Okay, once we have it into an augmented matrix, this time we do have to do some work, right? It's not as simple as the last problem. So what would be the first step that you would want to do here? A1, 2 of negative 2. And is there another step we can do at the same time? A1, 3 of 3, right? Okay, great. So I hope everybody's getting kind of efficient with these ERO steps. It really helps. The first row didn't change at all. 1, negative a, and 3. So I'm taking negative 2 times the first row and adding it to the second row in order to get a 0 there. So that's going to give me 1 plus 2a right there. And it's also going to give me a 0 over here, like that. Okay, and then I'm doing a1, 3 of 3. So I'll get a 0 here. I have to take 3 times the negative a entry and add it to this entry. So that's going to become b minus 2a. And then 3 times 3 plus 1 gives me 10. Okay, so we have that so far. So far, so good? Okay. So we need to, a lot of this has to do with kind of analyzing where the pivots are. Okay, so what would we maybe do next? First column looks great, right? So first column and first row are great, so what else could we do?
3 through 2 to 1. That way you can get rid of the 2a's on both the top and the bottom, or the second and third row.
So you want to multiply the first row by?
No, a 3 2 to the 1.
Well, that'll leave the 2a here. All that will do is change the middle entry it'll change the middle entry to b plus 1, I think. Because you're going to add this to this. That's what you want to do, right? You want to get rid of, this is not what you want right here. So how can we get rid of it?
Should do it the other way.
So the other way meaning you want to add this to this?
Yes.
So then you have 1 plus 2a here, and you'll have b plus 1 down here?
Yes.
Okay, so what? He seems very confident. Let's try it. So let's do a2, 3 of 1, right? That's basically it. So let's add row 2 to row 3, and let's see what happens. 1, negative a, augmented with 3. The second row doesn't change, but the third row becomes b plus 1 and 10. Okay, I just added the second row to the third row. Okay, still have this pivot here. What do you think? What are we going to do about that? Well, think about what all of your EROs are that you have.
Well, no, yeah.
How about if you multiply second row by 1 over 1 plus 2?
Okay, let's multiply the second row by the reciprocal of whatever that entry is. That's often how we get a 1 in that entry. Okay, so let's do that. Let's just basically divide by 1 plus 2a in the second row. That's going to give me 0, 1, 0 like that. And now the third row doesn't change. So we have this kind of a pivot structure. Okay, it's looking pretty good. Is this in row echelon form yet? What do you need to have underneath this one? A 0, right? So how do I get a 0 under there? I want to change the b plus 1 to a 0. So which of the three operations are you going to do? A2, 3 of?
Negative b minus 1.
That's right. Basically take the negative b minus 1 times the second row and add it to the third row. Okay, let's do that. We're going to get 1, negative a, augmented with 3, 0, 1, 0, and then 0, 0, and we've taken some multiple of 0 and added it to 10, so this is still a 10, right? And this is still a 10. So it appears, oh, that's still a 10, isn't it? It appears that we have ended up with what conclusion here? No solutions here, right? No solutions in this case. Does that make sense? Whenever you get a pivot to the far right of this bar, that's the situation when there's no solution. But wait a minute, I thought we were trying to do like 3 cases here. We ended up getting no solutions. Is there anything we've done here that makes anybody nervous? Deshaun.
I was nervous on the last step.
This one?
Yeah, I was nervous there, and just because at that point, the matrix right above it, right here,
Yeah.
at that point you can see that if you put B is, if B is not 9, then there could be solutions there. Like if B is 9, then you have 9 plus 1 equals 10, and that's a solution, as long as you find something.
Well, but you have 10 and 10 here, which can be reduced to 1 and 1. I mean, you still can do EROs and come up with basically the same thing. So there's everything is solid from here to here. This is the problem here, guys. The tricky thing you did here is you multiplied by a number, but that number that you multiplied by, does it make sense? Does this fraction always make sense?
Oh no, because A was
Negative 1/2. If A is equal to negative 1/2, do you see what happened? You divided by 0. So as long as A does not equal negative 1/2, everything we did was perfect. So as long as A does not equal negative 1/2, and B can be anything, we would be in the first case. So regardless of what B is, if A is not negative 1/2, there are no solutions. That makes sense? So almost always there's no solutions, which isn't really that surprising because there are only 2 unknowns, x1 and x2, but there are 3 equations. A lot of times when you have many equations and you don't have very many unknowns, you're going to end up with no solutions. So we could not, from here to here, we did an operation which would have been illegal if A was negative 1/2. In fact, come back over here with me. If A was negative 1/2, what would this matrix actually have been? Well, it would have been this, right? It would have been that would have been the matrix. If A was negative 1/2, that would have been the matrix. And so going from here to here would never have worked. You can't take this row of zeros and have it become 0, 1, 0, right? So that's the point. So if A does not equal negative 1/2, hi Philip. I think you're good right there. I think is he good up here? Right there? I'm setting up my camera is all. So
Want to move there?
no, probably not there. Maybe yeah. One of these chairs here is fine. Either one. No worries. No worries. Okay, so if A does not equal negative 1/2, everything that we did before is correct, and we get a pivot in the last column, the far right column, which means it is inconsistent. Okay, and I want to go back now and look at, well, what if A was equal to negative 1/2? Then this would have been the matrix. So let's, on this little piece of the board here, let's talk about, well, what would have happened in that situation. So, well, let's see. So if A equals negative 1/2, this is the matrix. What ERO are you going to do next based on this one? Okay, permute which ones? 2 and 3, great. So permute 2 and 3, we get 1, 1/2 augmented with 3. We get 0, B plus 1, and 10, and 0, and 0, and 0. So here is a pivot. Okay. So now what about what about the B plus 1 here? I claim that we're kind of we're going to need to go in 2 different directions here again, right? If B is equal to -1, if B is equal to -1, then what's going to happen is we're going to get, again, no solutions. Oh wow, so this is getting, I don't have enough room here to write this down. So if A does not equal -1/2, or if A equals -1/2, then we could still be in trouble if B was equal to -1. This is kind of a complicated one. Sorry. You have to just do this very carefully. So in either of these situations, you have no solutions. But if B does not equal -1, then would you agree that then this would really have been a pivot? And if that's really a pivot, then how many solutions do we have here? Are there any free variables? No, so there's just one solution, right? It's just one solution in that case. So case B, when is there one solution? Well, that would be if A is equal to -1/2 and B is not -1. And can we ever get infinitely many solutions here? I think we've exhausted every possibility, right? So infinitely many solutions? Never. It's impossible. Okay? This one's a little kind of complicated set of scenarios. I like the ones in the homework better, actually. I like the ones where there's only one parameter instead of 2 that are kind of intermixed. Or I like the ones where you don't have quite such a crazy set of EROs like we do here. So this is a little bit of a tricky one. But being able to do a problem like this would not be a bad idea. So this is off of the midterm review session questions. Okay? Everybody all right with that? Part of what the review session is for, guys, is you're not necessarily supposed to walk, well, if you do, it's great, but you're not necessarily supposed to walk out of here thinking, oh, I know everything, I'm ready for the test now. Part of what the review session is to sort of just expose you to some of the different things you need to be reviewing, and you will walk out of here knowing, okay, I'm solid on this, but not so much on that, I need to practice that. And that's why being here 3 days before the test gives you plenty of time to go back and get some of that stuff straight. Okay, let's try another problem unless there's any questions with this. You okay with this? All right, let's do another one. Can I use this board over here, Frank? Okay, I like this problem. This is number 4. Not in order of the review session questions, but it does say, without computing the whole matrix A inverse, find the 4-3 entry of A inverse. So I don't want you to find the whole inverse, I just want you to find one particular number where the matrix A is this matrix, 2, 0, -1, 3, and 0, 1, 0, -1, and 0, -2, 1, and 1, and 3, and 1, and 0, and 0. So let's take that matrix, it's a 4 by 4. find the 4-3 entry of it. I don't want to find the whole inverse. So, does anybody have any suggestion here? As to how we're going to do that. You have to think about like what topic, where in the material does this fit? So Edgar's talking about cofactors up here. See, if you so you think about A inverse. We have two ways of finding A inverse, right? That we learned. One is the Gauss-Jordan method from chapter 2. And then the second way is, well, it's using what's in the video, which some of you have watched, and most of you have watched, I think, which is the adjoint method. And so, which of those two approaches do you recommend we probably would want to use here? The adjoint method, because the adjoint method has the specific information about the 16 entries of this inverse matrix. The Gauss-Jordan method does not. The Gauss-Jordan method, you have to put the whole 4x4 matrix in there, attach the identity matrix, and you have to do all those ERO steps and work your way across. You're going to come up with the whole A inverse, which is what this says not to do. Don't find the whole A inverse. The adjoint method, though, focuses better on like individual entries. Let's remember, what does the adjoint method say? Again, if you watched my video, you already know this. Otherwise, I'm going to talk about it some more tomorrow in class. But that's the formula. You have to divide by the determinant of the matrix, and here's the adjoint, right? So here's the thing. If I want the 4-3 entry of this matrix, right? Would you agree that I basically have to find the 4-3 entry of the adjoint and divide by the determinant? And what is the 4-3 entry of the adjoint matrix?
Because we cross cofactor of 3.
So remind me again, how do I find the adjoint of A? Transpose?
Matrix.
You flip it, that's transpose. That's transpose. You transpose the matrix of cofactors. So the 4-3 entry of the adjoint matrix would actually be which cofactor? The 3-4 cofactor. That's exactly right. So in this case, the 4-3 entry of A inverse will be the 3-4 cofactors. You're just going to switch the rows and columns, right? And then you're going to divide by the determinant of A. That's how you're going to do it. The determinant of A is just a scalar, which you're dividing by out in front. Every single entry gets divided by that. Does that make sense? I like this problem because it's going to force us to do cofactors. It's going to force us to take determinants. But if I actually asked you to find the whole A inverse this way, you would have to do the process 16 times because there's 16 different numbers in the matrix. But I'm only asking you for one of the entries, so it's a reasonable problem. Okay, so we have to do these two calculations. Which one do you want to do first? I don't care. The 3-4 cofactor. Okay, let's do the 3-4 cofactor of this matrix. So remember how we do that. We go to row 3, column 4, that's this entry right here. And we cross off that row and column. Remember that? And then we take the determinant of the 3x3 submatrix after we cross off that column. That's what's called the 3-4 minor. Maybe let me write it over here. So the 3-4 minor is the determinant of the 3x3 submatrix. So I'm crossing off the last column. I did this in blue. It's a little bit light to see it here, but I want to preserve my matrix. So I've crossed off the third row and the fourth column. 2, 0, negative 1, 0, 1, 0, and 3, 1, 0. There is my determinant that I have to compute. How would you like me to compute that determinant? There are a couple of great ways to do it. One is with the arrow method. Are you guys really comfortable with the arrow method? If you are, then let's not do it that way, because that means you know how to do it already. I want to try and just show you how fast you can do it with the cofactor method. You can choose, remember the cofactor expansion method, you can choose any row or column that you want and expand along it. And this matrix has a couple of good choices, one of which is, I think, the third column. Right? So how do we cofactor expand, say, the third column? Well, we take the entries from that column times the cofactors for that column. So here's an entry which is a -1. And what is the cofactor for that entry? Well, I basically cross off the row and column. I have a little 2 by 2 here. What is the determinant of that little 2 by 2 matrix? AD minus BC, right? It's just -3. Okay? So I get 3. Do I have to change the sign on that? For this position in the matrix? No, because remember, guys, you do plus, minus, plus, right? So that's a +3. And see, if I'm expanding the third column, then when I go down, technically there's still 2 more terms, right? I still have to add, you know, A23, C23, plus A33, C33 here. But the thing is, those are both 0 because those entries are both 0. I can do this determinant in my head in about 2 seconds. I don't have to do the arrow method or anything. All I do, I look at this thing, I say, oh, look at the third column. It's almost all 0. The only entry that I have to calculate is the first one. I have a -1, and then the opposite, 2 by 2, is just -3. So I get 3. Okay? So this determinant, so M34 is 3. With me? If you don't like that, of course you can do the arrow method. That's also fine, but I really hope and think that it should be okay. Actually, later in the semester, just give you a preview. Later in the semester, you're not going to want to do the arrow method all the time, even for 3 by 3. The reason is that later in the semester, we're going to be dealing with matrices that have variables in them, not just numbers. And when you do the arrow method, when there are variables in them, you're going to end up with expressions that are harder to algebraically simplify. The cofactor expansion method is actually going to be your friend, even on a 3 by 3, just because it's going to set things up algebraically in a way that you can work with it better. So I just really want to emphasize, try to be working on that. Everybody okay with it? Can everybody get the answer of 3 just from expanding the third column? Here's the other way to do it. Expand the second row. So in the second row, I only have one number. It's a 1. I could skip this term. I could skip this term. I only have this one term. If I cross off the middle row and middle column, I get a 2 by 2 determinant consisting of the corner numbers, the 4 corner numbers, and if I do the 2 by 2 determinant for that, I also get 3. So actually that time, instead of getting -1 times -3, you get 1 times 3. And again, the 2 entry also has a plus, so you don't change the sign of that one either. So you're getting the same answer. It is so easy for you guys. If you're shaky on determinants, you can practice this, until 5 o'clock in the morning, because you just write down any matrix you want and try expanding different rows and columns. You have to get the same answer, right? No matter which way you do it. Just don't be too hard on yourself. If you write down a matrix that's like 4 by 4 and there's no zeros in it, it's going to be painful. So it's nice that there's lots of zeros here. Okay, so M34 is 3. So does that mean that C34 is 3? If we go to the 3-4 entry, look what we find. Sign change. Remember, that means there's a sign change. So this should be -3. The 3-4 cofactor of A, which is this matrix here, was -3.